right, welcome. This is the first episode of the Uptime Podcast. I'm your co-host, Dan Blewett, and I'm here with lightning protection expert Alan Hall. Alan, how are you?
Great, Dan. How are you?
Doing well. You're in self-isolation in Washington, D.C., and you're out in Massachusetts, right?
Out in western Massachusetts, it's a snowstorm right now. We're supposed to get 6 to 8 inches of snow today, so self-quarantining or self-isolation is going to happen no matter what. Though it's still in the midst of winter over here. So, you may guys have at least sunny weather south of us, but up here we're all burrowed in our holes. Trying to survive the winter.
Yeah, DC is not too bad. It's and that's what's been kind of eerie about the whole coronavirus thing is that there's been some really nice days recently, and it's 65 and sunny, and there's not a human to be seen, which is so weird, especially for this time of year where everyone's excited for spring and you just want to be outside on those days, but it's just a ghost town.
Yeah, we see a lot of people running up and down the street, jogging when the sun does come out. Even when it's moderately warm, they'll be up and running down the street. But they're self-isolating when they're running. Even so, instead of seeing the normal packs of college kids running down the street, right, you gotta spread out. So you got to be careful when you're driving down the roads because they're self-isolating when they're running too. So.
Yeah. So here on the Uptime Podcast, our goal is just to talk about the wind turbine industry and how we can keep these crazy big machines. Obviously, they keep getting bigger every year. With some of the challenges that these are facing, being in some of the harshest conditions, in the middle of the ocean, up on mountain ranges, in the snow, in the rain, in the sleet. This whole theme of uptime. If you're a wind farm operator, if you're working in the renewable energy sector, keeping these machines running is a huge challenge. Obviously, we have the technology to produce tons and tons of electricity, but can we actually keep them running 24/7 or as close to it as possible? So Alan, my first question for you today, because you've been in the lightning protection industry for 2+ decades. What does the common person not know about wind turbines? And as they keep getting bigger and bigger and bigger, now they're soaring. I know GE's new turbine is now over 800 feet
big.
Total, which is
big.
Crazy. How do we keep these things protected from lightning specifically?
Well, as they get taller, they become more and more of a lightning rod. I think if you just think, even the layman can kind of see that if you have any wind turbines that are around your home or business, you watch them get taller and bigger and produce more energy. Each one's producing more and more energy as we go along. And that's economies of scale sort of thing, right? You want to produce the maximum amount of energy in the smallest amount of footprint. So what's happening now is as we're getting taller and taller blades and turbines, is that they're becoming sort of lightning attractors in a sense. They're actually triggering a lot of lightning events. And the issue with that really is, if we're starting to trigger lightning events, they're becoming less random. So if a thunderstorm's coming through, there's pretty much, you're starting to approach more than 50% probability some of those turbines are going to be struck just based on their size because they're so high. And we're also putting them in places where they stand out more. Obviously, around us, we're placing them on mountaintops, which makes a lot of sense because that's where the wind is. But off the coast of Massachusetts and all around the world, we're putting them in the ocean. So they're definitely the tallest thing around. And it's just causing more and more lightning strikes. And as we're hearing, we're hearing about a lot of downtime just because lightning is damaging the blades.
So talk a little more on this concept, because I think, and this was a misconception for me, just sort of as a person new to the industry, you're saying that these are causing lightning strikes rather than just sort of being in the wrong place at the wrong time?
Yeah, that was the common philosophy forever, was if lightning struck your house, your car, your airplane you're in, anything, it was qualified as an act of God. That was pretty much the case. If you have me playing golf and out in the middle of nowhere and lightning hits you, it's kind of an act of God. But what's happening now is we're getting so tall, as those storm clouds come over, they're full of charge. And even if lightning would not normally happen, just because the proximity of a grounded gigantic object starts to trigger that process. So even though there may not have been a lightning strike before the storm got near the wind turbine field, the wind turbine field tends to cause it to start. And so what we're seeing is there's been a lot of good videos and things taken in the last 10 years, a lot of it over in Spain. But triggering of lightning events coming from the wind turbines reaching out into those clouds, physically putting electrical energy into the air and traveling up to the cloud and discharging the cloud. So it'd be kind of like rubbing your feet on the carpet and touching a doorknob. It's a similar sort of thing. Like you help start that process.
And those are streamers, right? So streamers they originate from ground objects, and they sort of reach out to step leaders. Is that right?
Yeah. So it goes from streamers. So what happens is you have a lot of electrical charge at the tips of the blades. As the energy gets, or the electric field gets stronger and stronger, you start to ionize the air, getting little things called streamers, which are just electrical discharges, and then they start to form into bigger things, and bigger things become things like step leaders, which are ionized channels that start to reach out in the air. So when you see a lightning strike out in the real world, not on in movies, but in the real world, what you'll see is these charge channels that tend to flash. All those is just charge stored up in the atmosphere as the electrical charge is trying to get from point A to point B. And that's what we're seeing a lot of on wind turbine blades is that the blade is starting that charge and reaching out to those clouds to discharge that cloud. So it's a really unique phenomenon. We spent a lot of time back in the 1920s and 30s when we started building big steel buildings, much higher than we had in the past. And those things were getting struck, and we just didn't know a lot about it. And like if you look back in old papers and things, you'll see things like the Empire State Building or General Electric instrument of the Empire State Building. And then we kind of forgot about all that, and then we started making wind turbines. And so we're sort of reliving the Empire State Building testing and phenomena. It's just the problem with wind turbines. If you're in the Empire State Building, you're in the middle of New York City, and if something were to happen to it, you could probably get to it pretty quickly and repair it. If you're out in the middle of nowhere in the ocean, or you're on top of a mountaintop with a wind turbine, it's going to take a little while to get that thing repaired.
Yeah, to say the least. It seems nightmarish to have to go repair some of these turbines. I mean, in like gale force winds in the middle of the ocean with it seems like a terrible ordeal.
Yeah, it takes a lot of training, a lot of safety training, because you can think about the risks involved of climbing out onto these things, and there's a lot of things that can go wrong. I'm always shocked at how good the industry is on the safety record for people working on the wind turbines. They do a really good job of doing it. It's just a really difficult job. So in our company, we're trying to help minimize the times you got to go out there to fix some lightning damage. That's what we're focused on, because it is just dangerous no matter how you look at it. If you're hanging from a rope several hundred feet in the air and you're trying to fix this blade, it's not an easy job to do.
Yeah, especially considering that these turbines are placed in environments, especially in the ocean, where there's just a constant flow of wind. I mean, being up on a rope while it's 35 mile per hour winds, that seems like the time when you don't ever want to be up on a rope. But that's just the reality a lot of times. Yeah,
well, they try to limit the times. They're not going to try to be out there when it's really windy, so they're going to be selected times they can get out and go do those things. I think the kicker is, if you've ever tried to work on a car or hanging from a rope, it's like that. Right, you just can't walk over to the toolbox and get a tool. It's got to be on you, and you don't really have any leverage either, because you're not really kind of attached to the thing. So it's like levitating, trying to fix your car.
Do people do that? Do people fix cars via ropes?
Well, if there was somebody in the world that could do it, it'd be a wind turbine blade repair person. That's who it would be. Because if you ever watch them work, it is really amazing. Just the coordination and the attention to detail and the thought process that goes into it before they even get onto the blade.
Oh yeah. You talk about just like a common job about, just like painting your house. They talk about, the biggest thing is prep. Like if you do your prep right, everything else goes very smoothly. But they're going to be up there for a couple hours at least, I would assume, for some of these more complex repairs. And they're going to have to have multiple batteries for their drill and their sander and their, all those cordless tools. They're going to have a lot of stuff. I mean,
There's a lot of stuff. Yeah. So you have a lot of equipment hanging off you also, right? So you're the one bringing the equipment in, you're the one taking the equipment out. It's a complicated thing, no doubt.
Yeah. So when these turbines get struck, obviously, the blades are the closest thing to the heavens, so they're going to take more often than not the lightning strikes. But
Yeah.
the nacelle gets struck.
Yeah.
Where else? How would you break down the percentage of strikes on these turbines?
I think the data, and I had been looking at data over the last couple of weeks, but it does tend to vary because you're not getting full industry data, and it's also going to depend on where you are located in the world. But it's roughly, from what I can see, it's 80-90% blades, 10-20% nacelles. So if you think about the back of the nacelle, you have instrumentation, kind of pointy objects hanging off the back of the nacelle, and then once in a while those things will get struck and miss the blade. But for the most part, as these blades get bigger and taller, the nacelle strikes are going to go down, and the blade strikes are just going to go up accordingly because the blades are so much higher than the nacelles.
Yeah. So, but I think what's really interesting is, and this is something I didn't know until just recently, is that the lightning's not going to attach to just the exact point when it hits. We think of lightning as being, it hits a tree and it splits a tree,
Right.
or it hits a lightning rod and that's where it goes in. But
Right. Yeah.
turbine blades are moving 100 plus miles per hour. So
Yeah.
it'll hit and it'll initially attach on the tip, but then that blade is still moving.
Yeah.
And so then it'll attach to a second point and maybe even a third.
Yeah.
Speak a little bit on how these actually attach to these moving blades.
Well, the thing to think about is typically during a thunderstorm, there are winds. And so the wind turbine is actually generating power in most cases, unless the winds get too high, and then they automatically shut down. But those blades are turning, and when they're turning at a speed that is longer than the sort of the lightning event. So what will happen a lot of times, it'll strike one blade, and then as the blade sort of rotates around down to the bottom, it'll jump to the next blade that's popping up in the air. That is pretty typical of the bigger lightning strikes. And so you'll actually see damage on two blades instead of just one. And obviously, short lightning strikes, little strikes will take mostly on one blade, but I've seen images and videos of them jumping over to second blades, and it's pretty common looking at the data. Obviously, we don't sit around, 24 hours a day, 365 days a year watching turbines, but the data is coming back indicates that the blades are moving fast enough that you're going to hop from one blade to another. So
Yeah.
a lot of the blades, if you look at them, have similar damage to them. It isn't like one blade's taking a big strike and the other two haven't. It's all three have some level of damage to them.
And that's, I think, where a lot of problems occur because, the lightning receptor, like every blade rolls off the factory, the lightning receptor pretty close to the edge of the blade, but not all the way to the edge or the tip. And then, so if the initial strike is out there at the tip, which makes sense, it's going to be the farthest point, up towards the sky. Great. It might hit the receptor, flow through the down conductor, then to the, into the ground through the rest of the metal body. But if it's got that second attachment point, then what happens?
Well, if it's jumping over to another blade, if that's what you're asking, if it jumps to another blade, it kind of starts the process all over again. We see this in airplanes quite often, because the airplanes are moving such a high speed, where it'll attach to the nose of the airplane. As the airplane starts flying forward, the lightning channel is fixed in space. So the lightning channel tries to find the next spot to attach to, and then the next spot to attach, and the next spot to attach to. So every attachment has its own sort of local physics to it about where it's going to attach to. So it may have hit the receptor on blade one, but when it starts looking for blade two, it's going to go anywhere it possibly can find. And it may not find the receptor on blade two before it finds like the down conductor or finds some sort of structural weakness in the blade and decides to go through it. So it's like rolling the dice all over again, right? So you want to increase your likelihood that it doesn't go anywhere but the receptor, no matter which direction it's coming from, whether it's starting there or it's being swept into it. You want to get it to those receptors. And we see that when, in a lot of cases, especially on sort of the restrike situation, where it doesn't necessarily go to the receptor on that event. It's the physics are a little bit different, and I think that's what's driving it. Is the physics get a little bit different, and once you have an established lightning channel and lightning energy running down into a blade, when it jumps to the next blade, it's more of a localized effect instead of a sort of a universal effect. So you get different kinds of lightning environment and lightning requirements. And we on the aircraft side, I know you bring up aircraft as an example. On the aircraft side, they actually have two separate lightning tests they'll run, sort of the initial lightning attachment to the airplane and then the subsequent attachments to the airplane, because the physics are different. We don't really do that on wind turbine blades. We look at the initial attachment and hope for the best. And I think the aircraft industry's learned from that over time, and the wind industry is starting to pick up a lot of those things as they figure out what's happening in the field.
Yeah. So as the blade moves, it gets initially struck, on the receptor on the tip, and then it moves a little bit and it takes a second strike. Say it's further down the same blade. So that's where a lot of the damage is going to occur. Am I right? Because it's going to try to puncture and go through to the down conductor that's hidden beneath inside the blade.
Yeah, so there's two places where blades are really susceptible. Anywhere where there's the big copper down conductor running inside the blade, and then a lot of times they have something we call a receptor block. So the actual receptor screws into a big aluminum or steel block that's mounted inside the blade. So the receptor block is physically much bigger than the actual receptor on the outside. So you see this kind of coin-sized receptor on the outside. Then you see this. It's probably talking in inches, probably 12 by 12 or 6 by 6 block of metal that's sitting on the inside. So that receptor block's just as attractive as the receptor itself in some cases. So lightning tends to get to those receptor blocks and tends to get to that down conductor cable, which in order to do that, it's going to blow through the structure of the blade, which causes all kinds of damage.
Yeah. But initially off the factory floor, the blade dielectric is enough to kind of keep that insulated. Is that right?
Yeah, I mean, if you go test a new blade, and which is what we tend to do, is we tend to take a new blade off the floor and then go off and run a lightning test on it. It's the same. We do the same thing for aircraft, by the way. An aircraft will make a plastic part, and it's just rolled off the factory line. We'll take it out for lightning testing. It's perfectly new. It's pristine, and when you go test it, it looks great because the dielectric, the actual physical nature of the plastic material, is still pristine. It hasn't been stressed electrically over time. And so a lot of times you get a great test result. And then as you put that product into service, it seems to degrade over time. And what we're seeing is that just being exposed to multiple lightning events or electric charge events or electric field events will degrade the plastic materials. And so they're not as strong as they once were. So that lightning test you ran, that you qualified your blade, and so you run off and you qualified your blade to meet the IEC specs, you're not going to get that same sort of performance out in the field, and that degradation of the dielectric and weathering is going to do that to you. So it in a lot of cases, you'll see a lot of great advertising come out that says, oh, we've done the lightning test, we've done the IEC testing, everything was great. And then a year later, you hear about the lightning strike that blew a hole in the blade. Well, that's why.
Yeah. And then does, things like rain erosion, just the temperature fluctuations, do those sort of hasten the process of the blade dielectric sort of eroding?
Yeah. So anything that eats into the blade degrades the blade. Be it hot, cold, stresses, mechanical stresses, forces, rain erosion. Is a big one, obviously, is it actually physically eats away at the outside structure of the blade. That removes some dielectric material and just makes the blade electrically weaker. Obviously, there's a big push right now to make the blades more durable for rain erosion and sort of being out in that, and particularly in the ocean, where the blades are getting beaten up. That degrades the lightning protection also. So again, we're seeing differences in what we test in the lab to what's actually happening in the field, just because of that.
Yeah, and that makes sense. I mean, it's hard to think of, for me as a layman to the, electricity world, it's hard to think of something being electrically porous, but for me, I'm just sort of visualizing it as like actually having holes where the electricity can actually go through, but it isn't really like that, but in a sense it is, right?
Yeah, and a lot of times, so in the power industry, they learned a long time ago to not make things out of plastic because they change their nature over time. If you look at, if you go out on the street and look at the light pole or the pole that's powering your home or apartment complex, whatever you're living in. You'll see that a lot of the components are made out of ceramic. They're actually out of a glass ceramic material. That's why, is that those materials don't really change structure over time, and they can handle the weathering, but they're also particularly brittle, right? So you can't use them to make wind, and they're heavy too. So you can't make wind turbine blades out of those things.
You
can make
hit a
airplanes
bird
out of
and
them.
just shatters or something.
Yeah, right. It's
pterodactyl.
It's the wrong material, but it just tells you that you don't see a lot of plastics being used in sort of the power industry, and that's why, right? So because those things tend to degrade with heat and temperature, UV. You pick it. Plastics do change substantially over time, and you know, this is a division of labor typically that happens in any sort of on the engineering side, right? So we all go to school, we crank out electrical engineers, and we all understand electricity and all that cool stuff, and then we create mechanical engineers. They all understand the stresses and the loads and the materials and all that kind of great stuff, and never the two shall meet, right? In the lightning world, you better be good at both of those, or better have an understanding of both those, because you're dealing with materials and you're dealing with electricity. And that's where sort of the handoff becomes a little murky, is a lot of times the mechanical engineers get involved, or structural engineers get involved on the lighting side, because it's so much in the structural aspects, and the materials aspects are so important, and the sort of the electrical guy is just running a test. Somewhere you got to meet in the middle. And I think that's part of the reason why we've had so much difficulty over time. It's just been that sort of separation of labor and the way we train engineers. But, as time goes on, it's one thing about the human condition is you learn from your mistakes, right? And so we're adapting like everything. And we're starting to see a lot of changes happen in the wind turbine industry, where we're starting to be a little more cross-functional, particularly in lightning. And we're starting to see more of the electrical, in my opinion, the electrical people are taking on some understanding of what the materials are. And that's a good approach. And I've seen a lot of mechanicals tend to be at least somewhat electrical savvy. Not that they can, create a circuit or make a microprocessor or anything, but they understand sort of the energy effects of lightning and what it does to materials. So we're getting there. It's not a fast process, but we're getting there.
Yeah. Well, and one of the things we're going to talk about in our next episode is just all the new waste that's being produced, because this is kind of crazy that, we're getting to the point where a lot of these wind turbines have been around for a long time, and they're starting to come out of service with some severe damage. You might have to take a whole blade out of service. Yeah. And what are we doing with this stuff? We've been facing that with cell phones and electrical waste. I mean, it's funny how our species is creating more huge piles of trash, but this is a growing concern for the wind turbine industry, and they're just now starting to figure out what they can and can't do, and how they can maybe repurpose some of these huge blades.
It's similar to a lot of different industries, especially the airlines right now are taking big time hits, and the aircraft manufacturer taking big time hits. And what's going to happen, and what we're going to see, and I'll give you the sort of equivalent between wind turbines and airplanes. So they're going to park airplanes, and then they will take airplanes out of service because they've met their service life. Now, in an airplane, a lot of that material is going to be recycled and made into something else, right? So a lot of it's made out of metal, or the parts of the airplane can be reused and used as replacement parts on other airplanes. So those airplanes are recycled forever, and you'll see them sitting in boneyards in the desert and recycled. A blade doesn't work like that. Once it's met its service life, it's really hard to extend it. And I'll give you a good example, like the B-52, which has been around since the mid-50s as a United States bomber aircraft. It's been around a long, long time. They will retrofit those things to keep them flying. And the same thing is this of some commercial airlines, is that a lot of airplanes have been around a long, long time, because it's more efficient to try to keep that thing in service than to throw it away. On the wind turbine side, we haven't really gotten there yet. When blades get structurally degraded, that's pretty much it. They're going to end up in a landfill. And that's the trouble, is that they're not, right now, the way we designed blades 20, 30 years ago, they're not really recyclable. So we're struggling. And so the more we can keep blades in service, the less we're going to be putting them in landfills. And I think it's a good thing to be thinking about. Yeah.
Well, Alan, great first episode. Next week, we're going to tackle this a little more in depth, this issue of, turbine blade recyclability. What are some potential, what can we do with these massive things that are getting bigger and bigger? One blade is now the size of a 20-story building. It's getting
They're getting up there. Yeah, it's getting crazy.
But yeah, so tune in next week for the Uptime Podcast, again, where we talk about everything wind turbines, renewable energy, and lightning strike protection. Alan, thanks again.
Yeah, thanks, Dan.
And
Stay
we'll
warm.
see you next week. I will.